In this video we will see what is open delta or VV connection. Figure 1 shows a closed delta and in figure 2 open delta is shown. As it's one of the phase or winding is removed, hence the name open delta. This is the closed delta. The terminals are marked as A, B and C. The voltage measured between the lines are called as line voltage. The directions of currents are shown. As this current is flowing from A to C, it is called as IAC. This current is flowing from C to B, it is named as ICB, and this current is flowing from B to A, it is named as IBA. Let me draw the phase voltages VAN, VBN, VCN, and the angle between each phase will be 120 degrees. From this, I'll try to get the line voltages. VAB is equal to VAN minus VBN. Minus VBN is obtained by reversing the phase VBN, that is shifting VBN by an angle 180 degrees. Now take the phasor sum of VAN and VBN. We'll get the line voltage VAB. Similarly, get the line voltage VBC and VCA. Now we got all the three line voltages from the phase voltage, and the angle between each line voltage is also 120 degrees. The angle between phase to phase is 60 degrees and the angle between phase to line is 30 degrees. Now let us consider the open delta. In this figure, the voltage across each winding or each phase is as shown along with the polarities. Applying KVL for the circuit, we'll get the voltage equation as plus VAB plus VBC plus VCA is equal to 0. Rearranging the above equation, we'll get VCA as minus of VAB and minus of VBC. Let me first draw VAB and VBC. This is the line voltages. Now get minus of VAB and minus of VBC. Draw a line exactly opposite to VAB to get minus of VAB. Draw a line exactly opposite to VBC to get minus VBC. Take the phasor sum of these two to get the line voltage VCA. Now you can observe very clearly here also we got three line voltages VAB, VBC and VCA. The figure 1 shows the line voltage obtained with the delta-delta connection, and this is the line voltage which is obtained during the open delta connection. From this you can observe that the open delta will also produce the balanced three-phase supply. Now further let us analyze the open delta connection. Here the phase voltage VAN and VCN are shown along with the line voltage VAB and VBC. Now obtain VCB, phase shift VBC by an angle 180 degrees. The current produced by the phases VAN and VCN lags by an angle phi with respect to corresponding phase voltages. The angle between IA and VAB is 30 plus phi, hence we can tell that IA lags VAB by 30 plus phi. The current IA can be written as IA is equal to I1 at an angle 30 plus phi. The angle between phase and line voltage is 30 degrees. The angle between the phase and phase current, phase voltage and phase current is phi. Hence we can tell that the IC leads by an angle 30 minus phi with respect to VCB. Hence IC is written as I1 at an angle minus of 30 minus phi. The minus because the power factor is leading. Let us find out what is the power, apparent power supplied by the open delta. VIA is the power supplied by the first winding and VBIB is the power supplied by the second winding. Replace IA and IB as, split these terms into real part and the imaginary part. Now take all the real parts on one side and the imaginary parts on the other side. where this can be written as 2 cos 30 into cos 5. Similarly, this term can be written as 2 cos 30 into sin 5, where cos 30 is root 3 by 2. Replacing that, finally we will get power supplied by open delta is equal to root 3 times V1 I1 at an angle phi. Now let us find out what is the apparent power supplied by open delta connection and delta delta connection. This is apparent power supplied by VV connection. The apparent power supplied by delta delta connection is given by root 3 VL into IL. Rearranging that, we will get 3 VPH into IPH. Taking the ratio of VV by delta delta, we will get this as 1 by root 3, that is equal to 57.7%. The power supplied by the open delta is equal to 57.7% of that of delta delta connection. From this we can observe one limitation with the open delta connection. In 3-winding system, if one of the winding is damaged or removed, the power supplied should be reduced by 1 by 3 times. Instead of that, the power supplied is reduced by 42.3%, which is 9% higher. Next point is the utilization factor. It is a ratio of power supplied during VV connection and to the power supplied when two transformers are operating separately. It is found that the ratio is 86.6. It means that the transformer will operate less than the installed capacity. If installed capacity is 100, it will operate at 86.6% of installed capacity. Next, let us analyze what happens if a third winding is added. The power supplied during VV connection is given by, and the power supplied during closed delta is given by. Rearranging the above equation, where this term is equal to SVV, or this can be written as, just by adding one transformer to the existing system or one winding, the power transferred capacity is increased by 73.2% than that of open delta connection. Last, load on each phase. The power supplied by the first phase is given by, and the power supplied by the second phase is given by. If phi is 0, assume that the phi is equal to 0. The first term will becomes V1 I1 into cos 30, and the second term will becomes V2 I2 into cos 30. Hence, the load on both the phases are same. Let us consider the next case. Phi is equal to 20. The first term will become 30 plus 20, that is 50, and the second term will become 30 minus 20, that is equal to 10. The power supplied by the second winding is V2 I2 into cos 10. Power supplied by the first transformer is V1 I1 into cos 50. It means that second winding heavily loaded when compared with the first winding. This is one more drawback with the open delta connection.